I'm Rick Alonso, and I'm a senior, a math major. And today I'm going to give a talk on the Galois Theory. So, before I start, maybe we should give some motivations. Polynomial equations is like one of the oldest ever in math, and which is still rich. So people want to looking for zeros of this polynomial equation. Is it too small for you guys? Is that okay? Yeah. Good? Nice. So let's go from different degrees. So for degree 1, n is equal to 1. So we have ax plus b is equal to 0. It's easy to get a solution for this, right? Or given a formula. It's just going to be, minus b over a. For n is equal to 2, which is also easy. I believe everyone knows this. We have a solution should be, can anyone tell me?
Yeah. Minus b plus or minus square root b squared. Oh no, minus 4 is c over 2.
How about for n is equal to 3? Do we have a formula?
Formula I don't know.
But the answer is yes, but I'm not going to write it down because it's a big formula. And the same for n is equal to 4. We also have a formula for this. And I think the cubic formula is proved by the Italian mathematician, Cardano. And this one is given credit to some other mathematician too. Like so how about n is equal to 5? I'm not going to write the equation, you guys know. Do we have a solution for this? The general formula? I see someone shaking his head. Yes, that's true. So we don't have a formula for this. So this is called A proposition, which states that there are no general solutions. There's no general formula for to solve a critical equation. And actually this is, we can do more, which is uneasy, bigger than fine. This is true. So this is proved by Ruffini and Ergo. But the proof by Ruffini is pretty long. But today we're going to use Galois theory to prove this. And another reason is the Galois theory can do better than this theorem. Because Galois theory can tell you specifically for one polynomial whether or not it's solvable by radicals. Alright. So suppose you have a polynomials with any degree. I assume it's monic because you can always divide by the first coefficient. And then suppose you have the root alpha 1, alpha n. Now we know roots exist because of the fundamental theorem of algebra, correct? And then we can have a look at the field generated by this root. You might, okay, maybe you don't know what the field generated by this root, but I'm just going to play it here. I'm going to explain it later. All right? Then, by Galois theory, there is a one-to-one correspondence, which is called the Galois correspondence. between the sum subfield of this field and the subgroup of the Galois group. So again, you don't know what's a Galois group, I'm going to tell you later. And this corresponds is order reversing. I'm going to say that later too, but I'm just saying. So the Galois group, what is the Galois group? It's just the group of permutation between the roots, so which is a subgroup of Sn. So for the Galois groups, we know whether or not the group is solvable. So we connect the solvability of the polynomial with the solvability of the Galois group. So which means, given a polynomial, it's solvable if and only if the Galois group, the corresponding Galois group is solvable. Okay? So it's a little bit complicated, but there are 3 parts I need to tell you to understand this. So how to generate this field? What is the Galois correspondence? And what is the solvable group? So first I'm going to tell you what is a solvable group. So you guys know what is a group, right? The group is just a set with an operation which is associative and it has an inverse and it has a 1. Okay? Hi. You guys can get confused at first. Oh, here.
It has 138 minutes of fun. Yeah, so multiple people can take pizza at the same time.
They just already did it.
Would you like a slice?
Nah, I'm kidding.
I put it in the corner. Right. So first, I'm gonna give a definition of solvable group. Definition: a group G is solvable if there exists a chain of subgroups say GI Gn to G minus 1 to G1 to G
such that gi quotient by gi plus 1 is abelian. And the second is should be normal. Yeah. Gi is normal in gi plus 1. So normal means any elements in G, G x G inverse, here in G. So another definition. A group G is simple if the only normal subgroup is G and the trivial subgroup which is 1. This is a definition. And I claim that A5 is simple. Anyone, do you know what is A5? Yeah. You guys know? So A5 is just the even permutation of S5. So what is S5? S5 is a group of permutations on 5 elements. Alright? So, to prove A5 is simple, it's easy. You just assume it's not simple. Then, by definition, there exists some other non-trivial normal subgroup. Let's call it N. And then you consider the order of N and the order of A5 quotient by N. Either one of them has to be too big or one of them has to be too small. That's just a rough idea, but or you can believe me, A5 is simple. All right? And there's another theorem. It says if G is solvable and G is simple, if and only if the G is cyclic. So a group is cyclic means it's generated by one element. And the order of G has to be a prime number. So together with this theorem, we claim that S5 is not solvable. So the rough idea is considering A5 as a subgroup of S5. If S5 is solvable, then you just take the chain of S5, consider the intersection of A5. Now A5 is solvable. And by this theorem, because A5 is simple, then A5 has to have a prime order, which is not true. Because the order of A5 is 5 factorial divided by 2, which is 30. It was not prime, so S5 is not solvable. What? I've heard some question. Yeah, never mind. Okay? This is a really important result we need for our main theory.
Yeah, actually, the question is 5 factorial over 2, that's 6.
Is that right? I don't know. Okay, you're right. My bad. It's not a prime. Sorry, thank you. So remember this. S5 is not solvable. Alright? Any questions so far? I mean, if you don't even know about group theory, just assume, just remember this sentence. S5 is not solvable. All right? Yeah.
It's cyclic and order is prime, right? Both of them, right?
Yes. And all right. Next. So I just finished the part with solvable groups, and then I'm going to tell you how to generate the field with a root. So a field is just a ring with 1, and each element has the inverse. So it's a quite nice ring. Next, I'm going to cover some definition of field extension. Again, if you know nothing about field, I don't know what to say. So first, suppose the chain of field. So which means F is a subfield of K and L, and K is a subfield of L. All right. Now we say L over K. By this notation, it means the field extension over K. And we define the degree of this. The dimension of L over K as vector spaces. So one example is consider C over R. Can anyone tell me what's the degree of this? 2. Right. Because you can consider C as a complex plane. The C is isomorphic to R2. And R2 is the dimension of R2 is 2 over R. Next, we say an element alpha in L is algebraic if it's the root of some polynomial. P of alpha is equal to 0 for some p as the element of alpha. Just basic definitions. Second is an irreducible polynomial. So a polynomial Ps over Lx is irreducible if whenever you write Ps as a factor of two other polynomials, let's say Qx and Tx, at least one of them has to be a unit. And because Lx is domain, the unit just means a constant. So one of them has to be constant. Alright? So you can consider it as a rough idea of prime number in Z. Yes. So now I'm going to tell you how to construct a field, but
adjoint root of the polynomial, given root. So we suppose Px is irreducible over Fx. And consider a field of extension K over F such that alpha is in K and alpha is the root of Px. So P of alpha is equal to 0. So we can construct F adjoint the root alpha in the following way, which is isomorphic to the quotient by Px. Px is just the idea generated by the irreducible polynomial. Oh shoot, sorry. The Fx. Sorry that. And you can, if you want to know why, you can consider the homomorphism from Fx to F alpha, such that we send any polynomial to F alpha, and consider the kernel. It's trying to give you this isomorphism. And one note is that the root of this Px is algebraically indistinguishable in F of alpha. When I say that, that means F of alpha 1 is isomorphic to F of alpha 2, where alpha 1 and alpha 2 are both the roots of the irreducible polynomial. Alright? And I have two more definitions. Sorry, there's a lot of definitions and information such that you can understand what is the Galois correspondence. So, because field theory is like a half semester course, so it's a little bit hard for me to cover everything. But yeah.
There's more pieces that you guys want.
So we let field F be a finite extension. A finite extension just means the degree is finite. Then we call K is Galois over F if the order of the automorphism is equal to the degree of K over F. And this extension is called the Galois extension. So I need to tell you what is the automorphism from K over F to K over F. So automorphism is just an isomorphism from the set itself to itself. And here, it's just the element element of K such that fixed F. So here it's a collection of elements in K that's fixed F. So this is the definition of this F. And this is called the Galois extension. There are several other, equivalent definitions. I'm just write it down if you know it. So K is normal and separable. This normal is not the same as a normal group. It's a normal extension. The third one is that F is equal to K over G. Okay, all right. So this means what we said is the fixed point of K under G. The fourth one is that K is a splitting field. Of a separable polynomial. All right. So why I want to mention this equivalent, because we're going to use the third definition and the fourth definition to construct some examples so we can understand it. Before I move on, I want to show you guys some examples. Again, let's consider C over R. Is this Galois? Is this extension Galois extension? Anyone tell me? Alright, so the answer is yes, because
Yeah, right, because like there's there's two Automarks.
the degree is 2. Let's say first, as I said before, this is 2. And you can consider C as R join I. And again, we consider here, we consider the elements in K, we consider the elements in C. That's face F. F here is just R. So we only have 2 elements, which one is identity map. The other one is complex conjugate. Z tends to Z bar. Remember, we want to fix F, so we want to fix R. So you have to consider a map from complex number to complex number that fixes the real part. There are only 2 such maps, which is identity map and complex conjugate. So the order of the Galois group is equal to 2, which is equal to the degree. So this extension is Galois. Alright? So far so good? Okay, so now we're ready to state the most important theorem of the Galois theory, at least the classical Galois theory. So which is called the fundamental theorem of Galois. So which states that so we let K over F be a finite extension. Oh, sorry, the Galois extension, of course. Then let G
denoted by the Galois of Q over F. Then there exists a bijection between the subgroup of K and the subfield of K and the subgroup of G. Let me write that down. So the subfield D of K containing F. So we write down a diagram. There's a one-to-one correspondence between the subgroup of G. So there's 1, A, G. So there's one thing you need to observe is that this one-to-one correspondence is order reversing, which means the larger subgroup corresponding to a smaller subfield. This is because if you have a larger subgroup, then you have more X, which means there are less elements in X. So, there's a less chance you can fix all X, all F, you see? Okay. So now we can study some examples. So this is the Galois correspondence, which we need to connect the group, the field generated by the root and the Galois group. So let's look at some examples. Oh, maybe I should ask you, if there are any questions? All right. Okay, so we already considered the example of C over R. Let's consider another example, which is Q adjoint square root of Q over Q. All right. First, let's see. Is this extension Galois? Look at the definition. You can use any of the definition. So one way to do it is by the first definition. All right, we can do that.
Well, they're all equivalent, so the last one is actually quite easy.
Yes, that's why I showed you all of them. If you want to know, right? So if you want to use the fourth one, it's easy to see. This is a splitting field of x squared minus 2. And this is separable. So this extension is Galois. But if you don't know what is a separable polynomial, you don't know what's a splitting field, we can just use the first definition. So we want to know the element in this that's fixed Q. So what are some possible automorphisms? Because we know the elements in Q adjoint square root of 2 are in this form, where A and B are rational. So the automorphism has to send an element like this to some element like this. And we want to fix Q. So the only possible automorphisms are, first, of course, the identity map is always an element that fits. The second one is A plus B square root 2 mapped to A minus B square root 2. Remember, we want to fix F, so we want to fix Q. What is Q here? The Q is A. We want to fix A.
And this automorphism is fully determined by the map of the root. So in that sense, then we know the minimum polynomial is x squared minus 3 is equal to 2. So it only has two roots, which is plus minus square root 2. So automorphism has to ascend square root of 2 to either square root of 2 or the minus square root of 2. So there are two elements. So the order of the Galois group is 2. And the degree of Q square root of 2 over Q is equal to 2. Because this is just the other place, and this is irreducible, which is just 2. This is the Galois extension. So how about another example? Cube root of 2 over 2. Is this Galois? Is this extension Galois? No. Right?
It is splitting field. Not splitting field.
It's not a splitting field. Because, yeah, it's not a splitting field. It's just an intermediate field of the Galois, the splitting field. Right? And I'm going to give one more example. After that, I'm going to show you the final result. So let's have a look at the final example, which is 2 over 2. So I claim this is a Galois extension because this is a splitting field of square this is a splitting field of this polynomial, and the degree is equal to 4. So the Galois group, the order of Galois is equal to 4. So we know the Galois group contains 4 elements, which is a permutation between the roots. And we know the roots are this. The roots of this polynomial are plus or minus square root of 2 and plus or minus square root of 3. Right? So the possible isomorphisms are identity, the inverse, and the two more morphisms. All right. And then we want to know what is this Galois group. Well, if you know some group theory, then if the group has order 4, then it's either claim 4 or leave 4. But whatever. So let's define some tau to be the map from square root of 2 to square root of 2 to 3 to minus square root of 3 to 5 to be square root of 2 to minus square root of 2 square root of 3 to minus square root of 2. So it's not too hard to check such that the tau square is equal to 1. 1 just means the identity map. Because it sends every square root of 2 to square root of 2, And then you send the square root of 2 again. So it doesn't change. Again, if it's a square root of 3, you send it to the negative square root of 3. And then you do this map again. It's sent to square root of 3. But you want to see the elements in this. Maybe you are more curious about this. And the elements. So the basis of this would be 2, square root of 3, and square root of 6, I believe. But when you have square root of 6, then when you apply tau, this is just equal to tau of square root of 2 times square root of 3, which is equal to tau of square root of 2 times the tau of square root of 3. So which is just minus square root of 6. So you apply this again, and it's identical. You see? Alright. A similar story. Phi squared is also equal to 1. And 5 tau is equal to the inverse, which is this map. And this is 5. This is tau, and this is phi squared. This is tau squared. So now we fully determine every element of the Galois group. The Galois group is just what? Identity element, tau, phi, and 5 tau. 4 elements. And if you know it, it's not isomorphic to the 4. It's called the M4 group, and which is solvable. All right. Also, I want to write down the one-to-one correspondence here, because here we know there's a one-to-one correspondence because it's a Galois extension. So let me do that.
So that part's not, you can't see that part on the camera.
Oh. So can anyone tell me what's a subfield of Q adjoint square root of 2 and square root of 3? Yeah, right there.
You would know square root of 2.
Uh-huh.
You would know square root of 3.
Uh-huh.
Q.
There's one more.
Q join square root of 6.
Yes. This is not your hard proof. And the degree of this is all 2. And they have the base field, which is 2. So everything here, they're subfield of the Q of square root of 2 and square root of 3. So they are all the subfield of K. Here K is just Q of adjoint square root of 2 and square root of 3. And they're all E here. And now let's look at the subfield of G. So what is G? What are subgroup of G? Can anyone tell me? Which is just the group generated by 1 and tau, the group generated by 1 and 5, and the group generated by 1 and tau 5. The order are always 2, so this is a group. And with a trivial stuff. Oh shit. Sorry. Because it's order reversing, so I should put in this. 1, 5 tau and 5 tau. The Q is corresponding to the previous group, the Galois group. And this is corresponding to the trivial subgroup. So this is a Galois correspondence. And I hopefully you guys have some understanding of the Galois correspondence after all the examples. Alright. For that, I want to bring the final result. As I stated earlier, that there's no general solutions for degree 5 polynomials, because almost all quintic polynomials are not solvable. So let's look at the example. So first, this polynomial is irreducible. It's not, you have to check. You can use Einstein. And then let the root be alpha 1, alpha 5. So we want, as I said before, the polynomial, the solvability of the polynomial is connected to the solvability of the Galois group. And it's connected to field extension, which is generated by this. So always have this picture in mind. So we first construct the fields. So field F, which was alpha 1 to alpha 5. Now we consider the Galois group. Working over rational. So we know it's isomorphic to some subgroup of S5. Why? Because it's a permutation. By definition, the Galois group is a permutation of the roots. And because it has 5 roots, so it's a permutation of 5 elements. A subgroup of a permutation of 5 elements. On the other hand, we say Q of alpha 1 the degree of Q of alpha 1 is equal to 5. So this tells us that about 5 divides, let's call this K. 5 divides the order of K over Q. And this is equal to the Galois, the order of Galois group. So 5 divides the order of the Galois group. Which means the Galois group G contains a 5 cycle. Alright? And also we know the 5 roots, it has, I believe, 2 real roots and 3 complex roots. So we know G also contains a 2 cycle, because it contains 2 roots. And then we need a lambda. We don't know. But if it's if a subgroup of S5 contains well, let me put it this way. S5 is generated by a 2 cycle and a 5 cycle. So we know G contains a 5 cycle. It also contains a 2 cycle. So that means G has to equal S5. So we proved the Galois group of this polynomial is not solvable. We're down here. So what does that mean? Does that mean this polynomial is not solvable? So which means there is no radical solution for this polynomial. and this is true for almost all degree 5, then of course there's no general formula for this. And for higher degree polynomials, it's the same idea. You first construct the field, and then you find the corresponding Galois group. And you just want to say if the Galois group is solvable or not to determine whether the polynomial is solvable. I think that's the main purpose of this talk. Any questions? Also, if you're interested, Galois theory nowadays is, I mean, the classical one is not super new or what, but there are still open research problems like the inverse problem, which is quite interesting, and also in the algebraic number theory, I think there's a connection between the Galois group and I mean, in algebraic topology, there's a correspondence between the Galois group and the covering space. In the algebraic number theory, there's a connection between the Galois group and the modular form, yes, the modular form. And actually, I think Andrew Wiles used that connection to prove very much that theory. Just to say. All right.
Thank you very much.
Thank you.